Okay, thanks. So thank you everybody for coming to my talk. So today I'm going to give like a very gentle introduction to high-dimensional expanders. So before we start writing stuff on the board, I suppose we all know expander graphs. These are like these extremely useful graphs that are like well connected, and like we have a lot of different ways to define them. And high-dimensional expanders are basically generalizations of expander graphs to like hypergraphs or set systems with more than just vertices and edges. We will soon see. These objects are like studied in discrete math, which is like where I maybe come from, but they're also studied in number theory and algebraic topology and like a lot of different places, which is very nice. And before we start, I maybe just could give a comment that like if later on you will like Google high-dimensional expanders, probably you will see like a lot of different definitions. Like a lot of different people mean different things when they say high-dimensional expanders. And this is like a nice phenomena because you can define expander graphs in many different ways, like spectral expanders or graphs without sparse cuts and so on. And it turns out that like the specific definition you choose, while it's maybe equivalent to other definitions in graphs, it's no longer equivalent once you go like up to higher dimensions. So today we're going to talk about like the most, like I think the most popular definition in like TCS, which is like local spectral expansion. And in fact, we'll even see like two definitions, but they will be equivalent. I won't give them like in the historic order they've got. I really want to like build something where we like sort of see where this definition somehow arises naturally in some contexts. So let me start by saying what are the high-dimensional objects that we will be working on, and these will be just simplicial complexes. So simplicial complexes are basically hypergraphs. So we have sets and hyper edges. Only the hyper edges may contain more than two vertices. And we have this like slight technical condition such that if I have a hyper edge T and I have a subset S of T, then S is also in our hypergraph. So I drew this in advance, so it won't be as my usual drawings. This is like my favorite simplicial complex. It's the fish complex because it looks like a fish. And when I draw this and I tell you that it's a simplicial complex, so we already see that it has like 6 vertices and 3 triangles. But of course, when I say that the triangle is apparent, then like all the edges are also appearing in my hypergraph. Okay, so they're also like first-class citizens. And like the vertices as singletons, they're also counted as edges. And in fact, like even the empty set, like formally from the definition, it should count as like a hyperedge in the hypergraph, although maybe this is slightly artificial. So like a slightly less maybe compact way to depict the same hypergraph is to look at its like Hasse diagram, where I'm drawing like the empty set, vertices, edges, and triangles, and so on. And you can see like the containment relation. This will be important for later. So there is like this very unfortunate convention where we call xi all the faces. Faces are just like the edges, but of size I plus 1. And like for me, this is an unfortunate convention, but this like comes historically from the fact that like simplicial complexes, before they were maybe an object in combinatorics, they were an object in algebraic topology. So like people really cared about like the dimension of the simplex and not so much about the size. So we sort of stuck with the fact that triangles are in X2 and so on, and we always need in our heads to like account for this like plus or minus.
So there is something wrong in X of 0, that should be X of -.
Sorry, yeah. Oh, thank you, thank you, Avi.
That probably was the main point of
Good. I invited this mistake because now I can also say, right, like the empty set, right, it has 0 vertices, so it has dimension -1. So like X -1 is always the set that contains the empty set. So this is like, this will actually be like slightly important for later. Okay, good. So these are our objects. And as we can see, of course, they generalized graphs, right? Graphs only have vertices and edges, and of course, if we have an edge, we have two endpoints. And one of like my favorite things to do in graphs is like to take random walks, right? So we start from a vertex, we choose one of its random edges, and then we traverse to a neighbor, and we repeat, and so on. And the thing that's nice about simplicial complexes is that it treats vertices and edges and higher dimensional faces roughly in the same way. So if in graphs we could have taken random walks on vertices, in fact, in simplicial complexes, we can do this also on high dimensional faces. So for example, I can take a random walk where I traverse from edge to edge if they share a triangle. So, you know, like if I say this explicitly, now I look at a new graph where like the nodes are the edges and I connect two former edges with an edge if they're connected by a triangle, but we all sort of understand from the picture that I start from an edge, go up to a triangle, and go down from to an edge. And I, of course, can also go the other way around, right? I start from an edge, I maybe go down to one of the vertices that it contains, and then go up to another edge. And in general, these are like different walks. So, like I like this diagram because it's sort of easy to like depict it like this, where the random walk on the vertices, like I start from a vertex, take a step up, and then go to the opposite vertex in the edge, and so on. And I can think about like doing the same thing here, where I start maybe from an edge, take a step up to like a random triangle that contains it, and then go down maybe to one of the other edges in the triangle. And like I do the steps up, I can also do the step down, and I can also go from triangle to vertex back to triangle, and I can do like a lot of things. So these are like the random walks that interest us. And like, you know, before I try to define high dimensional expansion with respect to these random walks, maybe let me just give some like some motivation about why we even care about random walks that look like this. So here are a couple of examples of where these come up. Well, first example is what we call the Johnson graph. So the Johnson graph has two parameters, n, and I'll write it d+1. Its vertices are just the subsets of some n element set of size d+1, or soon to be dimension d, and we connect two subsets by an edge if S1 and S2 intersect on all but one vertex, okay, on B vertices. So this is like a very classical graph in graph theory. But in fact, of course, we can view this graph as just doing this like maybe down and up again walk, or up and down again walk, with a simplicial complex that we will call the complete complex. And we'll also learn the notation from topology, delta ND. Okay, so this is the complex that formally contains all subsets of size at most d+1. So of course, this set over here, this is like all the D sets or D faces inside this complete complex. And this walk really, right, it describes me maybe going from a D+1 face down to a D face, and then up to another D+1 face, right? Because if I do that, I will just arrive at a random face that intersects my set with like D vertices. Of course, in the Johnson graph, this also corresponds to like going up, right? If I start from a D+1 face, go up to a D+2 face, as I wrote this here, they don't exist, but I can always take like one dimension more, and then go down back to D face. I will also arrive at some random face that has this. Now, like implicitly, you should also maybe ask yourself, but there's also like some probability that if I go down, I maybe stay in place because I go down to the same face. But these are good questions. Let's like ignore them for now. So I think that this example is nice, like for two maybe opposite reasons. First of all, using tools from high dimensional expanders, we can sometimes gain insight on like what's happening in this graph. So like you can like prove things on this graph, or like on variants of this graph, just by using like tools from high dimensional expanders that we will see today. And the second like opposite thing is that actually like the complete graph is like the optimal or like model expander graph, like the complete complex should, in our minds, at least be like the optimal or model high dimensional expander. So often it's the case that, people know things about this graph, for other reasons, like it's distance regular and transitive and so on. And like, you can prove a lot of properties on this specific like up-down graph of the Johnson. But then this is like sort of challenging you to say, okay, this is not really a property of the Johnson graph. It's maybe just a property of high dimensional expanders. And like by working hard enough and using different tools, I can maybe do the same things to reach the x's. So this is like one place that these up-down walks appear. Another place is, I don't know if we like to count or sample stuff. So let me give like a concrete example. Suppose we have some graph, let's call it H. And we want to sample uniformly at random or approximately uniformly at random a spanning tree inside H. This is like, I think, a very like basic sampling task. One can show that it's also like equivalent to giving an algorithm that like approximately counts how many spanning trees there are. And like one idea of how to do it, there are algorithms out there, but like one idea of doing this is maybe also doing a random walk that sort of is similar to this like Johnson random walk. So what do I mean by this? I can maybe, I don't know maybe how to sample a tree here uniformly at random, but I do know how to find a tree, right? There are deterministic algorithms that do this. So I start with a tree that's like very non-random, and then I will sort of gradually like change it in the same way that I do here. So like you look at like this graph where formally the like vertex sets are all the spanning trees. So I'll write it like subsets of the edges of H spanning trees. And I traverse from tree to tree by randomly changing one edge at a time. So like formally T1 and T2, I will connect them if they will intersect by all but one edge. So like, let's say we have, I don't know, D vertices, all trees contain D-1 vertices. So like I should intersect on D-2. So like taking a random step here is really easy, right? I only remove one edge and then I have not a tree, I have like a forest with like maybe two connected components. And now I have to choose another edge that connects between these connected components. And I can do this. But like doing this random walk, right, a priori, I don't know, maybe it gets stuck somewhere, maybe it doesn't mix very rapidly, but this is only a priori. It turns out that like using tools of high dimensional expansion, one can actually show that this walk mixes rapidly. So like this is actually a theorem by Anani, Liu, Oveis Haran, and Vincent. I don't want to like formalize things in TV distance and so on, but I just say that this like random walk mixes polynomial time in the number of vertices.
This was known
right.
for years. They proved the far more.
Yeah, thank you. Thank you for the comment. So in fact, like this is only like one example of the power of their theorem. In fact, their theorem generalizes not only to trees, but actually to bases of matroids. I'm not going to define what a matroid is. If you know it, then great. If not, it's just something that sort of looks like this, like that generalizes like independent sets and so on. So maybe we'll talk about this like more in the end of the talk. I just want to say that what is the simplicial complex that's behind here? And the simplicial complex in this example are just subsets of the edges that are like acyclic, that are forced. Let's see. And of course, this is a simplicial complex, right? I remove an edge from a subgraph that has no cycles, it remains with no cycles. And like the maximal sets are all going to be like spanning trees, which have the same dimension. And this is like not the only example one can give besides matroids. You can also model like colorings in a graph and like positions of particles in a solid and like many of these things using these random walks. So I hope I like convinced you that like studying these random walks is a good idea, and maybe like theory behind like high dimensional expanders could help us maybe study these things. Of course, we can also do a bunch of different things.
The theorem is for any graph H.
Yes. For any graph H, and I of course haven't given like the exact rate, but like it makes it fast enough that you can actually use this like random walk to sample something uniform or approximately uniform in like polynomial time. Yeah, so we have a lot of time ahead of us, so I think it's like if this was like an hour talk, then I would do things like more quick and dirty, but because we have 2 hours, it gives me time to actually like establish term notation and like motivate some like maybe basic definitions, but in the language that I like, which will make it easier on us afterwards. So I want to talk about high dimensional expanders, but I want to like define first what are like expanders in graphs. So we will see how we can actually like generalize them. So like for this, for now and forward, when I will define things and prove things, I will sort of assume that my simplicial complexes are like highly regular, which means that every vertex is adjacent to the same number of edges and triangles, and every edge is contained in the same number of triangles and higher dimensional faces and so on. This will sort of make definitions easier. You can ask me later what happened in the general case. Somehow it's not interesting. So suppose we have some simplicial complex X. Let me denote a set of functions that have real values on the I faces by Ci. And of course, you know, if X has a graph structure, we can also define like the adjacency operator, which the adjacency operator of the graph, I hope you've seen this before, takes a function on the vertices and gives us back a function on the vertices that sort of averages out the original function on the neighbors. So like A0 of F at point V, right, it averages F at U, where like V and U are together an edge in the graph, or like a one-dimensional face in the simplicial complex. Just in a show of hands, like, did somebody like, did anybody like not see this before? So I can go quickly. I don't have to.
It's not obvious in the higher for graphs. These are really the neighbors.
Right.
For higher dimensions, it's not clear whether you mean they are neighbors if you go up or they are neighbors if you go down.
Yeah. So the way I've written this, right? I mean that I give you this vertex V, and now you look at all the edges that are adjacent to V that contain V. So they're like V and U, and then you average out the value of F on U.
You want X1, not Xi.
Yes.
Okay.
So
this
is the adjacency operator.
Yeah.
Now I'm just thinking about graphs. I may have higher dimensional structure. This will soon generalize. Okay. Great. So some fun facts about the adjacency operator. First of all, so first of all, like this space, I like to think about it as also an inner product space. So we have also like this down here. Like I think of the inner product between F and G. Like now let's think of Ci. Like if F and G are I faces, I just think about this like inner product as just summing over F of S and G of S, where S are I faces, and like in the regular case, this is just like 1 over the size of Xi times the sum of all these. In the regular case, you need to put weights here, but don't think about it. Like in the non-regular case, this is not exactly true, but let's stick with the regular case, as I said.
One comment, what you call adjacency operator is what is also called sometimes the random walk matrix.
Yeah,
or
exactly.
a graph.
Right, so it's like I like to say operators, but of course operators and matrices are the same thing. You can write this as a matrix, which in regular graphs it's just like 1/d times like the adjacency matrix, like the matrix that says if U and V are adjacent or not. Yeah, so back to this adjacency operator with this like inner product over, of course, the vertices. If I look at like F inner product with G, this gives me this like nice, it's giving me this like nice bilinear form of summing over all the edges in my graph of FU, G of V. And in particular, this is also like self-adjoint and so on. If I apply this operator on the constant functions, it will of course give me the constant functions. And because it's self-adjoint and so on, if I have a function that is like perpendicular to the constants, which just means that its expectation or sum is 0, then like A will also be perpendicular to the constants. And when I define high dimensional expansion, I would like to sort of maybe define it as an operator norm of this function, but like it acts trivially on the constant function. So like the operator norm will always be 1, this could be shown. So I really want to like define it as like the operator norm of A, like restricted to functions that are already perpendicular to the constants. So, so this is actually a definition. Let's call like the two-sided expansion of a graph A, which I will denote like lambda in absolute value. So some people call it like the second largest eigenvalue in absolute value. I'm gonna write like two equivalent expressions to it. So one expression is indeed taking the operator norm of A, but when I restrict to functions that are perpendicular to the constants, okay? And the second one, which will be useful for later, is just spelling this out, this operator norm, which is like the maximum of A0 F inner product F divided by the inner product itself. This holds like because A is self-adjoint, and like just believe me maybe that these definitions are the same. I mean here also that this is of course different than 0. And like when this like lambda quotient is very small, we think of like the graph as being a good expander, and it like it's very similar to like what's going on in the complete graph in like a very nice sense. There's also like a one-sided expansion definition, which we can call lambda A without the absolute value, where you do the same maximum only without taking the absolute value on the numerator. I will like interchange between these two definitions, although they're not equivalent. And so I hope that most of you have seen this definition in some place previously. And at least believe me, it's like exactly the definition of like the second largest eigenvalue in absolute value, if that's the definition that you know. I'd like to say something that maybe you haven't seen about this definition, is that actually this sort of measures the operator norm distance between A and the adjacency operator of like the graph where like every two nodes are connected by an edge, and you also have self-loops. So like if let's call it J, if you look at like J as the adjacency operator, what I'll call like the complete graph, but with self-loops. Okay, so what is this adjacency operator? You get a function and now you average out over the neighbors, but everybody is a neighbor. So like J applied to F will just give you like a constant function, which is like the projection of F to the constants. And so it turns out that if I want to like,
There is a matrix is a constant.
like it's an all,
matrix,
yeah,
or
it's all
one
ones.
of them.
Yes, yes. I'm sorry that I'm moving away from matrix notation. It's a good idea to maybe remind this.
Do what you want.
Yep. And I can, like, you're hostages for the next 2 hours. So what I just wanted to say is that if I look at the operator norm of A with functions that are perpendicular to the constants, because this thing is like the projection to the constants, I can really write this, and this is really like the same number, just the operator norm of A minus J. So this is like, the expansion is really measuring in a precise sense, how different am I from the complete graph. So it's not surprising that like when this two-sided expansion gets smaller and smaller, then our graph starts to behave more and more like the complete graph. It starts to behave pseudo-randomly and so on. So this is like expanders, but we've come to talk about high-dimensional expanders. And so we sort of need language to, express this like up and down steps. So it turns out that you can express all these walks by just composing like two types of operators. They won't be from like C0 to C0, but they will be like from Ci to Ci plus 1 or back down, like the adjoint. So these two operators, we'll call them up of I or Ui, which goes from Ci to Ci plus 1. And like its adjoint, I would call Di plus 1, that goes from Ci plus 1 to Ci. And what they do is not a mystery. So Ui starts with a function on I faces and end with a function on I plus 1 faces. So what does it do to I plus 1 face t? Well, it just takes expectation over the s's that are contained in t, that are of course in xi, of f of s. Let me write this explicitly. This is just like 1 over I plus 2 sum over f of s, where s is like in xi and contained in t. So like the up operator from vertices to edges is a function on the edges. At like this edge, what it does, it like averages between d and f, and so on. The down operator does the exact same thing, only like in the opposite way. It averages what it sees from above. So like di plus 1g, it's now an I face, and what it does is it averages over all the I plus 1 faces that contain this. It contains this like input face. So I think these are natural operations. And like I should say that
contains the.
you
changed.
no, I think
you changed it. No.
Yeah. Okay, I'm gonna use like
I'm sorry.
I'm gonna use the convention that like if the letter becomes before in the alphabet, then it's a smaller set. So that's how I remember that like T is supposed to be larger. Anyway, I just wanted to say that like this expectation, while here I could always have written 1 over I plus 2, because like every like set with I plus 2 elements, you have I plus 2 subsets of 1 element less. Here, this is like, it depends on the regularity of the complex, and if the complex is not regular, then this is like a weighted expectation. But so I'm not gonna write it, but in a regular complex, it's at least like proportional to the sum of all of these elements. So it turned out that when I compose these two elements together, these two operators together, I will exactly get these like the adjacency operators, only for the graph that traverse from edge to edge via triangle or edge vertex edge and so on. So just to give an example, so suppose I take U0 and compose to D1. This is supposed to give me the adjacency operator of the graph, right? So let's see like if this really happens. So I put a function on the vertices, u0 transforms me to a function on the edges, and then I go back to a function on the vertices by d. So it's getting input v, and now I'm looking at the definition. D1 of a function at point v, right? It's all the edges that contain this input v of u1 f u0, sorry, thank you. I should say, I'm really sorry if I get like confused in indexes. My mother, she always got confused with the names of me and my brothers, and I was like, when I was a kid, I was so angry when she did that, because like, what, you don't like me and you don't even remember my name? And apparently it's like a family condition that everybody in my family sort of says one thing and means the other. I also sometimes like get confused in like lesser equal or greater equal, which, so ask me if you think that something is confusing. So I'm on record here, so sorry, mother, for being angry when I was a kid. Anyway, back to this here. So I'm doing u0f at point uv, which of course averages out, right? So let me write this over here. I won't use expectation notation. This is just half of the time f of u and half of the time f of v. So what am I getting here? So this is actually half of the time doing the adjacency operator on f at point v, and half of the time just doing f at v. Like b1 u0, like half the adjacency, half the identity. Exactly. It's a lazy random walk where you stay in place half of the time, which in retrospect, right, it shouldn't surprise us because we start from a vertex. Now we take an up step, right? So we go to like a random edge. But in the way I compose this, like the down step doesn't remember that I took an up step from this vertex to this edge. So it just sort of says half of the time I'm here and half of the time I'm here. So in particular, half of the time I go down to the same like vertex. Yeah. So in the same way, one can show that like if I look at ui the I plus 1, then this will be, yeah, so it will be 1 over I plus 2, the identity, and I plus 1 over I plus 2, the what I'll call non-lazy up-down operator. Let's write this AI is the non-lazy up-down. So what I mean is like the A1 non-lazy up-down operator goes from edge to triangle to edge, but it never stays in place. So basically, what's to be said here is that like analyzing the composition of these or analyzing like the non-lazy up operator, basically it's the same thing, and we will like take advantage of this later. As for the composition in the other way around, right? If I first do di plus 1 and then I do ui, here, like, I'm doing the down up, but I maybe don't have like such a nice formula for laziness and so on. Like if the graph is regular, the laziness maybe depends on the regularity, right? Because it depends on how many I plus 1 faces does the I face C. And like if the graph is not regular, I don't even have that. It will depend on like the specific vertex. And in generally, this is like maybe less nice. Like fortunately, the down up and the up down should like behave the same, at least spectrally or in many ways. So we'll also take advantage of that. But one thing I do want to maybe show is that if we do d0 on u minus 1, we get back to like this independent walk. Because if I go down from a vertex here, it doesn't matter where I went down to, I always go down to the empty set and I always go back to one of these vertices. So taking us like the down up here is just like doing a step in the independent graph. And actually this is like a very good hint on how we should define high dimensional expansion, because we already said that in like graph expansion, we're measuring like the distance between our adjacency operator and the independent walk. So in other words, we're sort of measuring the distance between this like up-down walk that takes into account the edge structure and this down-up walk that takes into account no structure. So like initially when one maybe wants to define high dimensional expansion, they might think to themselves, maybe I should talk about like expansion of this non-lazy upper walk. It turns out that this is not the idea that gives you enough strength. We will maybe talk about this very soon. But it turns out that the correct way to define high dimensional expansion, at least with respect to these random walks, is to say sort of that this non-lazy upper walk will be similar, at least spectrally, to the down walk, maybe with laziness. So, I mean, in the upper walk, again, as we saw before, like when I take this step in the upper walk, I will always have some intersection. So this can't like expand really well. Again, maybe we will see this soon. But like sort of the best thing I can say is that when I go from say edge to edge via triangle, at least like other than me having an intersection, which is like going from edge to edge via vertex, I'm not gaining very much information by the fact that it actually went through a triangle. Maybe
an example of something that's not an expander where there is a difference that's easy to.
Yeah, like here in the fish complex, right? This like this edge vertex edge walk is like connected, right? But this like edge triangle edge walk is disconnected, right? If I'm at the tail of the fish, I never go to the head. So this is actually an example of like a non-random walk expander. Maybe I will write the definition and then we will talk about like examples of HDXs. So yeah, so this will be like a definition that I will put a flower here because it's like the definition of the talk. So let's say that X is a d-dimensional simplicial complex. This just means that it has sets of dimension at most d. We say for lambda between 0 and 1 that X is a lambda high dimensional expander if the non-lazy upper walk and the lower walk on I faces, which is the u I minus 1, differ at most lambda in operator norm. Right, so I'm just taking the definition of expander graphs interpreted like this, but extending this. And this should be like for I equals 0, 1, 2, up to d minus 1. So this should happen in all levels simultaneously. So a simplicial complex, it may be very well connected on this level, but still, if you look at the levels above, it may be like not very well connected. So
This generalizes that one.
exactly, exactly. So that's like my first point here. It's like let's see that this definition is a good idea. So maybe give this a headline. Good idea. I don't know. So first of all, as Zev, as you said, generalizes graph expansion. second thing that I wanted to emphasize is that, right, we look at like the complete graph as sort of our model here that we're trying to sort of imitate or approximate. The complete graph is indeed a very good lambda expander. Lambda behaves roughly like the dimension over n. Complete graph in a high dimensional expander. We'll not do like the exact proof, but you can see that like if the non-lazy upper walk and the non-lazy lower walk are actually the same, because like if you don't account for the probability to stay in place, you're always just going to another face with like the appropriate intersection. Then like this definition only will maybe differ by like the amount of laziness in the lower walk, which is supposed to be very small as I take the number of vertices to infinity. So maybe just believe me on that. Yeah. And like, you know, okay, so it generalizes graphs. It behaves like our model, and it's at least powerful enough to say something about the mixing or the expansion of these like upper walks. So right, so I said that I want to say something about this, right, like the expansion parameter of the AI. And right, I mean, I want to say that if it's a lambda expander, then this will be less or equal to lambda, or maybe k times lambda, or I don't know, some function. I can't. Unfortunately, this thing, the only thing I can say about it is that it like mildly expands, or like, as I said, the graph becomes more of an expander as I go to 0, but actually if I take the dimension up higher and higher, this thing actually looks like 1. But still it gives me some expansion.
Lambda time I plus 1 out of that.
Yeah, it's lambda times the I plus 1. Okay, but in fact, this is optimal. So maybe I will write this. So this is actually a theorem by Tali Kaufman and Izar Oppenheim. Okay, where if X is a lambda high dimensional expander, then spectral expansion of these non-lazy upper walks is at most I over I plus 1.
So you wanted to say that it's that.
Yes, and I will also say as a claim, this is not a theorem, this is quite simple. Lambda AI is always greater or equal to this minus something that goes to 0 as we take more and more vertices. Okay, so at least in large simplicial complexes, this is essentially the right thing to ask for. I want to prove the theorem, and then I want to prove the claim, at least to lie about it a little. I'll go there. I'm not going to give the theorem that Tali and I'm not going to give the proof that they gave. They gave a proof that's, I think, more complicated, but also gives you a bit more. I'm going to give like a very simple proof that, in my opinion, it also sort of enlightens how like high dimensional expansion plays nicely with induction on levels of the simplicial complex, and it's like a really nice definition to work with technically. So let's prove this theorem.
For this to be interesting, lambda has to be less than 1 over I plus 1.
Yeah, you're right. Like that's annoying. Yes, for this to be true, it needs to be less than I plus 1. I can't recall now if this is also like tight in lambda or not. I mean, a priori, you can say maybe I don't have a high dimensional expander, or not a good enough high dimensional expander, but this like mixing works, and I think that's true. I mean, it's not an if and only if.
So if lambda is less than 1 in the definition,
Yeah.
you will have some mixing in the AIs?
No.
No. I mean, I can't prove. I can't prove it. Like for this, for this thing to apply, I actually need that lambda to be like very small in comparison to the dimension.
But it doesn't mean that it will be disconnected or something.
Right. It doesn't mean it does like the opposite doesn't hold, but it's just that I don't know how to prove it in general. And I mean, it could be the case where like for some complexes, like this doesn't hold and the walk still mixes, and some maybe not. Actually, you know what? I will say you can do a slightly better proof where you sort of account for different lambdas in different levels. And actually that is like kind of useful. I mean, in all these like counting versus sampling results, like in trees and so on, like the matroid case was like the simplest case to analyze, and it was like the breakthrough was really like connecting these two fields together. And then they like sort of started to look at other things like Glauber dynamics and a lot of things like in there. And then they saw that like, oh, I can't prove like for the same lambda, the same bound, but now if I like sort of take into account different lambdas, I can still do something. So, right, this is not completely tight. There will be some error that you will account for when going from level to level, which we will see in the theorem.
But in practice, you can make lambda as small as you want with a bigger degree.
There are some.
Oh, okay. So that's great. I love that you gave this comment now. Like it depends, right? In practice, if I'm looking at a complex that I want to analyze, then I mean it's there. It's either it has this lambda or it doesn't have. Like the spanning tree complex. I don't know, right? I mean, like the looser this theorem is, like the harder I need to work to maybe prove something, or maybe I can't, right? But like if you want to like use this as a gadget and like just like to construct a high dimensional expander, now if I allow like the degree of the vertices to grow larger and larger, here degree is just number of edges maybe connected, then I can get lambda like as good as I want. So there are bounded degree families of high dimensional expanders with a lambda as good as you want. So at least if you want complexes like this that are even sparse with bounded degree, then you can have them.
This is analogous to using expanders in our collecting codes. You need lambda to be small enough. And you have expanders with lambda small enough that degree. That's if you are allowed to bring your own expander.
Yeah, exactly. But this is also so annoying. Like sometimes you're not allowed to bring your own expander, and then you like you lose things with dimension. But maybe this is also inherent because it's inherently a more complicated object. At least in this proof, we will see like that the loss in the dimension is inherent because we're going to accumulate errors from down up. You know, maybe before I prove the theorem, I maybe just like hand wave a bit because I like this. I mean, what's going to go on here? I'm going to look at the expansion of like the non-lazy upper walk. But because of high dimensional expansion, I can say, I might as well look at the expansion of like the lower walk from one dimension below. But then all I need to remember from linear algebra that like in operator norms and things like that, it doesn't matter if I look at like the norm of like doing down up or the norm of doing up down. So then I say, oh, the norm of like this down up walk is like the norm of the up down walk that came in before, up to the laziness, which is like very easy to account for. And then I will continue and say, oh, this thing is like this thing from below, up until I get like to my base case where I'm like a good expander. And there I will lose errors both that depend on the dimension and on lambda. So let's prove this.
Dimension what will give you
The I over I plus
I over I.
Yeah. And the lambda will give me the lambda times I plus 1, which is like the number of times I accumulate an error. It's all morning like that.
Some,
Yeah.
yeah, there's some alerts.
Okay. So I'm going to prove the theorem by induction on I, the dimension of like this random walk. And for I equals 0, this is just the graph case, right, where we know that high dimensional expansion is equivalent to expansion. So lambda of A0 is at most 0 plus 1 time lambda. Okay, so is the base case clear? This is just exactly what we need. And now let's assume for I and show for plus 1. So what do we need to show? Right, so we need to take some function on I plus 1 faces, which is of course perpendicular to the constant functions. And is it still written here on the board? Oh, I wanted to write it here, but I forgot. Never mind, I will remind this. So I need to take a function that's perpendicular to the constant functions, and I need to show that like the random walk operator, the adjacency operator on F, inner product F is less or equal to, right, whatever I need to show. It's like I plus 1 over I plus 2 plus I plus 2 lambda. And I'm going to make my life a bit easier. First of all, of course, like this inequality is homogeneous. I can just assume that the denominator is 1, right, by like scaling. So let's do that. And also, for simplicity, I'm only going to do this. This is like the hard part, okay? Doing the lower bound, you can either do the same thing, or you can actually observe that AI plus a tiny bit of identity is like non-negative. This is like really the hard part, so I'm only going to do that. Great. So now, like, right, I want to bound this expression, and what I know is that AI is very similar to the down-up operator. So let's call this star. So what I'm going to do is I'm just like gonna like push the right expression in here by just doing this. Yeah, so of course, sorry, I needed AI plus 1 here. So the right indices here are like di plus 1 ui. Right, so all I'm doing is like adding and subtracting this term from the expression. And now, you know, this thing by high dimensional expansion, an operator norm, this is at most lambda. So really, I'm only looking at the down operator.
Hold on, I lost it.
Yeah.
Star is AI.
Sorry. Of course. This was supposed to be I plus, right? I'm assuming for I and proving for I plus 1. Sorry, mother. But yeah, right, I'm looking at AI plus 1 and I want to show that it holds using my induction. So I'm just like adding and subtracting the like associated down up walk on the same set of faces. Okay, and now like from this bound on operator norm, this is at most lambda, and I really need to bound what the down operator does on F. But now like from basic linear algebra, I know that when I look at the down operator, I can just look at the composition of these two in like the reverse order, which is ui the
The norm of a product of matrices doesn't change
exactly
with the order you multiply.
Yes. I don't know what the matrix is. I only know operators, but of course that is.
People have more.
No. You're right. This is correct. The norm doesn't change if you multiply two matrices on the left or on the right. And as we said, this is like an operator norm, maybe with respect to some like subspace, but still. So this is like that. But what is this now operator on one dimension less, right? This is like lambda of 1 over I plus 2 identity plus I plus 1 over I plus 2 of the operator that operates on one level below. And so this from the induction hypothesis is at most 1 over I plus 2, which comes from this identity term, plus I plus 1 over I plus 2 of lambda of the thing that came from below. And now the rest is like calculation. You put the expression here, you do like the calculation, you add this lambda. Now we maybe not to write this down. So star will at most be I plus 1 over I plus 2 plus lambda times I plus 2. So that to your question, even here, this is not exactly tight. You can get something that looks a bit better here, but essentially you will get like a linear dependence on I, which again is inherent because on every level you're gaining a lambda error. So I hope you appreciate how like simple this proof is. It's like I did it in like 4 or 5 lines, but it's a 1-line proof. Yeah.
So is the lambda high-dimensional expander definition, is that also equivalent to the supremum of a Rayleigh quotient for AI, like restricted to functions orthogonal to the image of UI minus 1?
So you also need that, like, if you look at AI on the kernel, then it will also be small, right? Like on the kernel of DI. Like it's not enough to be similar on the image of UI, like of UI minus 1, right? You need to also be like, you also need to shrink everything that's in the kernel of DI, right? Is that?
It's just a bigger space to work in the orthogonal complement of.
Yeah.
Just one way.
Yeah, I mean, in the 0 case, you know automatically that like A0 on like you know that like A0 on the constants, right? It does exactly what like the independent thing does on the constants. But here you have like different functions. Like what I want to say that it's not equivalent. You can decompose to like the kernel of UI of DI and the image of like UI minus 1, and you need to act the same on like both. The same means different things maybe in different spaces.
Yeah, I'm just trying to connect this with the like Durham Laplacian, which I think can be written as a supremum Rayleigh quotient over some subspace.
Yeah. Okay, so actually that's a good question. But I don't think I have like the tools to like appropriately explain this. We will see that this definition is actually like equivalent to what's called like the local spectral expander definition. And I think that you can also show, at least in the two-sided case, that's like it is equivalent to also saying something about the spectrum of the Laplacian. But like at the top of my head, I'm not sure if what you said is equivalent or not. I need to think about it. Great. So we also had our claim, which I also wanted to show because maybe it will also give us some extra intuition on these walks. That basically this is optimal. And in order to prove this, I just want to maybe give sort of a subclaim that is like something that is like well known on expander graphs. And this subclaim, maybe I will say this on the board. What I want to say is the following. Suppose you have some cut, Okay, so here you have the set of B, and here you have a set of B complement in your graph, and your graph is an excellent expander. Then if this cut has like a small side, say B is a very small side, then if you choose a random vertex at B and you take a random step, then most likely you will get out of B in that random step. Namely, like the graph expands, the all like cuts like this are supposed to be dense relative to the size of one of the cuts, which is just to say that if you're in a small set, you took a step, most likely you're not in that small set anymore. So I'm gonna write this claim as just an inequality. So for every B in our vertex set, which in this case,
For graph I is 1 or
for a graph, I is 0.
I is 0.
Yeah, for a graph, this is
Yeah, there's no
nothing.
boundary.
Right. Right, because for the graph, the right thing is 0 here. So, yeah. So my subclaim says that for every B, erase this, the probability of choosing two I phases according to the SWOC, I will write it this way. Like the probability of staying inside B, given that you started inside B, is at most lambda AI plus the probability of B. Here, when I say probability of B, I just mean the size of B, like this, because our complex is regular and so on. Okay, so like if B is very small and our graph is a very good expander, namely lambda is small, then the probability of staying in place is small. So like the contrapositive will be like using this to upper bound lambda. So I'm going to show a very small set where the probability of staying in place is large, and therefore lambda of AI will also be large. I actually use this side of the board.
Lower bound.
Yeah, sorry, lower bound.
We know what you mean.
Yes, fortunately. Okay, so like, what B should I take? Does somebody like have an idea? Like, okay, from the proof of the theorem, we saw that like the I over I plus 1 comes somehow from like these lower walks that have laziness, and like I'm accumulating this I over I plus 1 gradually as I go down, or I get it from below. So somehow, at least intuitively, it seems like the set that I should take here is a set that like comes from below. So like what we're going to do to prove the claim, we're going to fix some vertex, let's call it V naught, from the lower levels, and we're going to look at B, which will be all sets exactly that contain this vertex. So right, so if I look at probability of B, so let's say, right, this is like the size of B divided by xi plus 1. So let's denote the size of B as R, like for the regularity, for the number of I plus 1 faces. Wait, which, no, sorry, I need I faces. The number of I faces that are containing this like specific vertex, and like this is regular. So this is like, you know, this regularity divided by, so how many I faces do I have? So I will count them like this. I'll take the number of vertices times the regularity, but I counted every face like I plus 1 times, so I need to like divide by I plus 1 because I'm looking at I faces. So this is like I plus 1 over the number of vertices, or in general, a very, very small set. By the way, I don't really need regularity here. It only makes life easier. I can always find a set with like this bound on its probability. Okay, however, like let's examine the probability of staying inside B. So suppose, you know, I started by sampling S1, and I'm given that S1 contains V1. Now I'm doing this like non-lazy Upwork. So at the first step, I went up to T, which is like adding an extra vertex here. I don't know how I added it, but I went up, right? So I haven't lost this vertex V0, so I'm like still containing it. And now I have a bunch of options where to go. So there are I plus 2 sets that I can go down to. Of course, I'm non-lazy, I can't go back down to S1, so I have I plus 1 sets. But note that the probability of losing this V0 is only 1 over I plus 1. There is only one set, which is like T without V0, that doesn't have V0. So like really the probability of staying in place is exactly I over I plus 1. Like no matter which space I came up to, this is so like this is an inherent problem in high dimensional expanders. I will also say in a very informal language that in high dimensional expanders, essentially these are the only problematic sets. Like if you have a set that like for low dimensional for like low dimensional faces, it looks like pseudo-random. It doesn't have like a component that looks like these V's. Then your sets are supposed to mix like very well. This was proved by Hot, Moshkovitz, Mintzer, and Sattler for the complete complex. And after a while, this was like this was one of these like global hypercontractivity results that were sort of generalized to high dimensional expanders. So I don't see Siki here, but this was actually like her theorem together with Tom Gur and Noam Lifshitz, and it was like also proved roughly the same theorem was like proved by I forget. So it's Mitali Wafna and Max Hopkins and Shachar Lovet and Tali Kaufman, and I hope I'm not missing a name. I'm sorry if I am.
So these sets are called Dikstein.
Yes. In the language of global hypercontractivity, this is like a dictatorship because like membership in the set is only like determined by like this V, and you can also talk about like low-level juntas, which come from the edges, and they have essentially like the same behavior. But once you don't look like a set like this, then you're supposed to like expand really well. Yeah.
You don't look like this, it's called the function of row sensitivity.
Yeah, or it depends right where you come from. Some people call it pseudo-random sets also. Yeah. Are we taking a break? I think it's a good place.
It's up to you, so yeah.
Yeah, let's take like a 5-minute break.
5 minutes break.
Okay. So I want to continue. I had a good question in the break that sort of said, okay, this is like a nice definition or something, but like it's maybe hard to work with. And I mean, it's a good concern, right? I mean, I told you that I want to like bound maybe spectral expansion of this upper walks. So now I like invented this definition where I say the upper walk is like the lower walk, and you know, when you invent a strong enough definition, then you can prove anything from it, right? But like, why is this a good idea? And like, I put here number 4, which is what I'm going to do now, is that in fact this random walk definition that to me makes sense on a global level is actually equivalent to a local definition that like if you are given your day-to-day simplicial complex, you will actually be able to verify this often, I won't say quite easily, but often it is not as hard as this definition. So for this definition, I need to talk about what's called links, which are supposed to like generalize neighborhoods of vertices, only they will have more structure in the simplicial complex. So let me give the definition. So suppose that X is a d-dimensional simplicial complex, which sets of at most size d plus 1, and suppose I have a set X with codimension at least 2, okay? So the link of S, sorry, is going to be the following graph. In general, it's a simplicial complex, but let me only define it on the graph level. So we'll have vertices and edges according to sort of membership together with S. So the vertices of the link will be all the vertices in the complex, so that if I have a disjoint union of them with S, then the resulting face will be in xi plus 1, and the edges will be defined on the same way. So these are all edges, so that if I take a disjoint union of them with S, it will be in xi plus 2. So
it's a conditional hypergraph on containing it.
yes, exactly.
All way everything doesn't contain S, and you are left with whatever you are left.
Exactly.
And then you can
Exactly.
remove S from the names of
Yeah.
everybody contains.
Right, so it's exactly what Ali said. Let's maybe like look at this example also, that we'll see that we understand this. I'm looking at this E, right? And like, what are the vertices of the links? They correspond to edges that are adjacent to E. So for every edge, I take these 3 vertices, but I also have triangles. So every edge in the link will correspond to a triangle containing E. So I will also have like this edge and this edge. So the link of E will look like this 2 path. You know, if I look at the link of C, then it will look like these like 2 disconnected components, each one of 2 edges, and so on. And like the second most important definition in this talk will actually be that X is a lambda local spectral expander. So I will write LSE if for every face S, the lambda of the adjacency operator of the link of S will be at most lambda. Okay, so AS is the adjacency operator of the link graph. Okay, so in other words,
Normal, the second eigenvalue of this graph.
yes. So I can also give like the one-sided definition where I only ask for the bound on the eigenvalue from above, and you can do both variants. They're actually not equivalent to one another, but both are good definitions for local spectral expanders. Yeah, so this is like I'm giving you another definition of high dimensional expanders. You should also like try and verify that this is also like a good idea according to what we talked about before. So first of all, what about the complete complex? It's not so hard to see that the link in the complete complex will just look like a complete graph. So it will be like a very good 2-sided and like even a 0 1-sided spectral expander. So like the complete complex is like is also good in this definition. Also, does it extend the definition in graphs in like a very silly way? Like if you look at the link of the empty set, then this is just X, or at least like the graph of X, the way I defined it here. So like in particular, if the link is a 1 or 2-sided expander, this like this should hold, right? Then it's also like a local spectral expander. So sorry, the other way around. If you're a local spectral expander, then in particular, your like underlying graph is supposed to be a good expander. So like maybe it's kind of silly, but like this also generalizes the notion of graph expansion. And I'm going to give myself credit for this theorem, although I should only deserve half the credit, or like 1/4 of the credit, but for only half the theorem. And the theorem really just says that this local spectral expansion definition is at least qualitatively equivalent to the random walk definition when the dimension is fixed. So if you have a lambda local spectral expander, then you are also a lambda high dimensional expander according to the random walk definition that we talked about before. And it turns out that the converse also holds. So if you're a lambda high dimensional expander of dimension D, then you are also a something like 3D plus 1 lambda local spectral expander. This appeared in a work a couple of years ago, but like even though we were the ones that like formally proved this this side, this was actually like done implicitly in like a lot of previous works, not exactly for these up-down operators, but like the technique was already there and you really only needed to like plug in the correct operator. So I will also write Garland here, where like he's done basically the same proof, only like in a different setup. This second item is like a bit more technically involved, so I don't want to show it today. I only want to show like the first one.
Maybe I missed a sort of question. So the links are graphs or the complexes?
Yeah, so as I defined it here, the links are only graphs. You can also like define them as complexes, but for the like the link expansion definition, you are only looking at like the adjacency operator of the graph. So I didn't want to
comment. Also equivalent if you ask for the complexes to be high dimensional expanders locally.
So I mean, what does it mean to be high? Like that the links of the links are expander graphs, but like a link of a link is also a link in the original simplicial complex. Like think about like you're looking at your complex, now you're taking the link of E, and inside it you're taking the link of D. This will exactly look like the link of DE in the original complex. So what you're proposing is actually the same definition because like the links are the same, you're only naming them differently.
So sorry, the definition of lambda on the left, so for every S in X, you mean every S in X of I for some I less?
Yeah, every S in X of I, where I is at most co-dimensional 2, where like X is like 3-dimensional. Like, of course, like if I don't even have a graph structure, I can't expect anything from the link. Yeah, it's a good comment. I don't have to do much about today, but I think I will actually manage to do two of the things. One is I want to show you like the first item from this theorem. And two, I want to sort of analyze with you like the link of this like spanning tree complex, because I think that the link has like a very neat description that we can all sort of respect. So let's do the proof of the first item. And the proof of the first item basically comes from the fact that like links, as Avi said, are like these conditional simplicial complexes, and I like to think about them as localizations. And like doing something locally is also something that we can do with distribution. So let's look at the way I sample an edge according to the like non-lazy upper walk, and I'll show that I can do it equivalently in actually two ways. One of the ways is the one that you expect. I first sample a vertex from xi uniformly at random. Then I sample some t that contains it in xi plus 1, and then I go down, right? Then I sample like s2 in xi, conditioned on it being contained on t, and not equal to s1. So this is like, you know, I'm sampling a vertex and a random edge according to the non-lazy upper walk. But the point is that I can also do this using like my links. So now I'm thinking about sampling by first sampling sort of the intersection between S1 and S2, then sampling an edge in the link of the intersection, I can call it X and Y, and then taking like S1 to be this intersection plus S and S2 the intersection plus Y. So I would think about it as sampling R and Xi minus 1, sample an edge in the graph of the link, and then taking S1 to be R union X and S2 to be R union Y. X and Y are vertices, but I'm like writing the set notation is annoying, so I'm sorry about that. Okay, and the fact that I can sort of localize this distribution will sort of help us in showing this equivalence.
So you're really writing the adjacency operator, or AI is an average of local adjacency operator of the link.
Well, yes and no, right? I mean, it's not that I'm writing AI as like 1 over something, sum of like AR, because these operators aren't even operating on the same space. So morally, what you're saying is correct, and we will see precisely what I mean.
You can reduce them to the same space if you want.
I guess you can formalize it that way, but somehow it's less natural to me to think about it. I mean, yes, I am averaging. I am averaging, but I like to think about this more as like conditioning or something. But we will see what I mean. Okay, so back at our theorem, right? We have a local spectral expander, and we need to prove like that, right? So we want to show that like AI minus the appropriate down up is less or equal to lambda for the appropriate lambda. So again, what do? We take a function over the I faces, and again, let me assume that it's normalized, and what we want is to show that like AI minus DIU I minus 1 FF in absolute value is less or equal to lambda. And again, I'm not going to do two sides because they are similar, so I will do this like without the absolute value, which is actually the same as showing that AISF is less or equal to lambda plus. So I want to write here like the up I minus 1 down I FF. I'm just going to use the fact that they're adjoint, like the up and the down walks are adjoint, to like remove this and just put here the IF on this side. So is that okay? Good. So now the whole point, as Avi said, is that we're sort of going to at least morally average out on like the adjacency operators of the links. So we're starting with this like AI F inner product F, and we remember that this is like F of S1, F of S2, where S1 and S2 is a random edge according to this walk. When I say a random edge, I mean like a random pair of I faces that have like an I plus 1 face and so on. And now like the spiel is that when I'm sampling this edge, I can like condition on first sampling that like intersection, and then I'm looking at like sampling X, Y in the link of R, and then I'm going to put here F of R and X, F of R and Y. So now allow me just to like put some notation. FRX is like F of R union X. Okay, so what I'm really having here, right, is like the same expectation over R's, but what's going on here inside? I'm summing over the edges, or taking expectation over the edges of FR of X times FR of Y. So what is this actually? What am I looking at?
The link of R.
Exactly, I'm looking at like this bilinear form. I'm looking at like AR acting on this like localized version of the function FR, inner product with FR, right? So like formally write FR, I'm only defining it over the vertices of R. And now like this one inner product is actually an average of like many local inner products. So this is like averaging, locally averaging the adjacency operator. And now the rest of the calculations I'm going to do is really going to only amount to this. So now I know that like AR is like a very good spectral expander. It's a lambda spectral expander. Of course, FR is not perpendicular to the constants. So I sort of need to write FR as like its projections to the constants. Let's call it alpha R plus something that's perpendicular, call it FR perp. And skipping over like a few steps, like you can actually say that this is like an expectation of like alpha R squared, which comes from like the non-perpendicular part, plus this expectation of AR FR perp. And now basically, because this thing is perpendicular to the constants, what you get here is like that this thing is like at most lambda times the inner product of F. So actually it's like at most lambda the inner product of FR perp with FR perp, but FR perp is like a projection to a lower dimensional space, so like the square norm cannot, it cannot increase. So what you get is like expectation over R over this alpha R squared plus taking out the lambda, expectation over R of like this FR. And again, by like the same like localization argument, this is really just going to be the global inner product of F with itself. So I'm getting here like this lambda plus whatever I'm getting by these like alpha R's. So, okay, I started with...
This is the regularity, but otherwise you would, the fact that the average of the local function is the global.
Like if it's not regular, then it's still true for some, like, but yeah, for the regular case, this just follows from what you say. Yeah, so I wanted to show that thing up there. Now I got like a lambda plus this, so hopefully this expression will mean like this DIF, and that is indeed like the case. Okay, I'm gonna. What is this alpha R, right? It's the projection of FR to the constant functions inside R, right? Like I wrote it like up there. So what is supposed to be this like projection? This is just taking expectation. So here I'm looking like at expectation of over all the vertices in X0 of like FR of X, right? That's like the projection, but FR of X, recall that it's just like writing F of X union R. So now just by change of variables, this is just like sampling faces S in Xi that contain R and looking at F of S. So what did I get? This is just taking F, applying the down operator, and assessing at point R. Right, if I look back at the definition, this thing was defined to be this. So really what I get here is like DIFR squared, which gives me what I want. So it turns out like that because this DI is doing like an average downwards, this really captures the projection of the function to the constants after I localize to the link. So this is like a reinterpretation of what this down operator maybe means. So, I mean, really like maybe there was a lot of calculations here, but I think that the most important step was like here above, because this sort of occurs again and again in high dimensional expanders in like many distributions, where you have like your favorite distribution on like the global complex, which looks like this, and then you sort of like appropriately interpret it as like choosing some intersection, going like something in like the local link, and then you get like these things, which sort of make it sometimes convenient to work in this local definition. So that's maybe all I wanted to say about the equivalence.
So in particular, this implies that if you have a graph, all of whose links are expanding, then the graph is an expander.
Yes.
Which is not obvious at all.
No,
As a priori, it's the same proof.
yeah.
Yeah, so that's a way to construct expanders. Only that in most graphs we know that we want to be expanding. You look at the link of a vertex and you find an empty graph. So some of these are really weird expanders which have a lot of local waste.
What if you think that this joint union of two high-dimensional expanders, the link will still be expanders, right?
The link of the empty set.
Oh, the link of the empty set. So it has to be an expander to begin with for this definition.
No, for this definition, I didn't say anything, but like local spectral expanders also imply connectivity.
No, but they need the same lambda at all the levels. So the empty set link has to be an expander by the definition. First thing you have to check is that the.
Okay.
No, it's a trick to go.
Yeah. Okay, so I should. Right, you have me jumping ahead in this talk. I didn't want to actually like give like a very large emphasis on this, but Avi's like actually referring to the fact that it turns out that like a link expansion trickles down. Like if you know that like all your vertices are good expanders and your graph is like connected, like it's not completely separated, then the graph will also like be a very good expander. So like this also like trickles down from higher above. If like links are on this level are good expanders and links on this level are connected, then like these will also be good expanders. So it's like really.
So you can't take two expanders and connect them locally with some in some local way so that the links are expanders, but it's not an expander.
So that's a good question. Like even without considering the specific construction you're saying, the answer should be no. At least not. I mean, maybe not entirely, but you won't get like expansion as good as you want, because you could take two expanders that locally look like a tree, right? Like in every ball, maybe they have high girth. And then like you say, okay, I'm going to connect them by like some way, matching the vertices, doing something with the neighbors. But sort of your construction should only work if these were indeed expanders. They won't, it's not supposed to work if like you took something that's not an expander, but locally looks like a tree and you're trying to do your construction.
Let's say if I take two expanders,
yes,
that where the links are expanders. So local
where the links are expanded.
Yeah.
Okay, yeah.
And then I connect them in a local way.
So it will be a problem, right? I mean, what does it mean a local? Here you have like your high dimensional expander, and you know that like every link is a good expander, and you also have like this mirror.
I'm just saying there's no way to combine them locally in a way that's locally still an expander.
No, that's
I mean.
Okay, yeah, I don't see it intuitively.
No.
That's the beauty of the subject.
Okay.
Change the link.
I mean,
no, but there's a way to do it carefully, locally, and not ruin the.
I mean,
What do you mean?
no.
You cannot.
It's a good question. I mean, it depends on what you mean by it depends on what you mean locally. I mean, a priori, maybe if you know something about the neighborhoods here and the neighborhoods here, and you connect them, then maybe you can like
take a random small set here, a random small set here, and connect them with the complete.
I mean, that's a good question, but
why doesn't that?
Well,
even if it
With the
Even if
minute you
it's-
add edges, the link change and
Yeah.
you may not.
For every vertex, I change the link by
It
one.
doesn't matter.
I have an isolated vertex.
You can't take,
So if I just add an edge,
Yeah,
the link will have an isolated.
You ruin the link.
like, the thing that you're afraid of is like, you maybe are improving like global connectivity when doing like this, but then like on the neighborhood of the link here, once you added this vertex, then you shouldn't have added it like only once. You should have like also connected it to a bunch of things in the neighborhood. So maybe you can. It's a good question. I mean, there are constructions where you can take like two expanders and combine them together. Like you can think of like a tensor product for graph, just for like high dimensional expanders. Most of the time, like this maybe increases your degree, and you can say that it doesn't like, and it doesn't hurt your expansion, or it doesn't hurt it too bad. It's a much harder question, like in general, how to manipulate high dimensional expanders than the question to manipulate expander graphs. I mean, first of all, they're like more complicated objects, and second, like we haven't worked on it like a long time, right? Graphs, like expander graphs were what, 70s, 80s, when they were constructed in the first time, and then like, you know, the zigzag product was like a huge breakthrough where like you could suddenly construct these combinatorially. And here, like a lot of the tools that you have to sort of manipulate and construct expander graphs, they sort of break when you try to do it like this. So there are sort of natural barriers in just like taking graphs and trying to construct from them expander graphs locally, but maybe I don't want to like get into that subject too much. Also because it's sort of hard to say something precise. Okay, so maybe the last thing that I do want to do is to sort of give at least sort of a rough sketch on the theorem by Anari, Liu, Oveis, Haran, and Vinzant, where they sort of analyzed the links of this tree and show that these links were actually good expanders. They are good expanders. They're good one-sided expanders. Like the two-sided definition is trickier. It actually does depend on the matroid, but everything that we've done here so far, actually, it only applies for one. Like it also applies for one-sided expanders. So this is like really what you can do there. So let's call this maybe a lemma. So X is like the spanning tree complex for some, you know, for some graph H with the vertices. Then X is so I will write like a lambda equals 0 LSE, but like in the one-sided definition where you don't bound things in the spectral norm, you only bound like one side of the spectrum. Yeah, so actually I'm not sure if like they proved it this way, but I want to give a proof because like the links are really, they have like a very easy description because of like these properties of trees. And like, this is like the main building block in their theorem, not only for trees, but for matroids, because using this like local spectral expansion, they use the fact that like you also get like high dimensional expansion in like similarity of the random walks, and then they got like their optimal spectral bound, which in turn implied mixing and so on. So let's look at like how a link actually looks here. I think it's like a very nice example, like to get some like hands-on experience. So for simplicity, that's so our complex is like B minus 2-dimensional, where like B was the number of vertices. Also, I will like assume the graph is connected just for simplicity. So now let's look at the link here. And for simplicity, let's look at a link that's exactly in codimension 2. Okay, so it's a forest, not a tree. It's like a tree where we removed 2 edges. Okay, so how does such a complex look like? Look like? Well, right, we had our graph and like S sits under a tree, so it's a tree and we remove 2 vertices, 2 edges. So if we have like our whole graph, then actually the graph spanned by S looks like this. We have like 3 distinct connected components, right? Because like, and any 2 edges that go like from here to here and here to here, or like for any other, this will like construct a tree. So like the underlying graph that is spanned by S looks like this. So how does the link look like? What's like, so I'm saying the vertices in the links, but these are actually edges in the graph, right? So like, what are the edges that together with S still form a forest, right? It's either edges that cross from this part, if there are any, or from these 2 parts, or from these 2 parts, right? I can't have an edge that goes inside, but any one of the edges that crosses the 2 parts are perfectly good edges. So maybe I will like abuse some notation and write that this is like B0 times B1, or you know what, I'll use like B, Bi, Bj, is different than J. And we all understand my meaning. And what is like the edge? What is like the edge set? When are 2 edges also compatible with S? Well, they're compatible, right? If and only if they don't go between the same 2 components, right? Because if I have an edge from here and an edge from here, it will complete S to a tree, right? But I can't take 2 edges from the same component because then I will be disconnected, or I'll like equivalently I'll have a cycle. So these are all like
It's a complete hypergraph.
exactly. Maybe I will just draw it now that we know it. Here I have like the EB0 B. I'll draw it bigger. I'll have EB0 B1, E B1 B2, and E B0 B2, and between every 2 components, you'll have like the complete bipartite graphs. Okay, and this is a graph that's like very easy to analyze. Like in fact, like the adjacency operator of this graph has the same spectrum of the adjacency operator that just of a triangle. Here maybe I'm assuming regularity, but you can still get the same things. Where here, like you can write this adjacency operator as like just this like kind of matrix, and you can actually like compute its eigenvalues directly. This is like a conjugate to like P1 minus half P minus 1. And like in any case, you can also like show directly that, and this is like a 0 expander by like also other elementary means. Like all I wanted to show like here is really that like the link has very nice and like structure that we can exploit, and that even though like, you know, you say to yourself, wow, I need to show something about all the links, it's probably super complicated. Sometimes you get lucky and like the links are actually pretty simple. So Avi, you sort of ruined my surprise before. I wanted to maybe ask, how do I go from like this D-4 case to the general case? And actually there are 2 ways. One is use like this trickle down theorem where you say that if links of this dimension expand, then you will also get like expansion on the links below, and that will work. In fact, like in the matroid case or the spanning tree case for that matter, you can show that like links of even dimension lower, maybe they will have like more they'll have like more connected components here when you look at S, but essentially the link will just be like an inflation of like this, instead of a triangle, another complete graph with maybe more vertices. So you can really like also analyze this completely elementary, in completely elementary tools without using the trickle down theorem. Maybe this is like all I wanted to say mathematically. So let me just end.
You state the trickle down.
Yeah. Yeah, I can say, let me just state like the basic version. So this is a theorem by Zal Oppenheim. Also like the same techniques were used sort of before, and you can also sort of track this idea back up to maybe even Garland in the 70s. And this is like, suppose that X is a simplicial complex, let's say two-dimensional, and suppose two things. One, the X is connected as a graph, and two, for every vertex in X, XV is a lambda expander, then the expansion trickles down to the whole complex. So then I'll write lambda of like the link of the empty set, or like the expansion of the underlying graph, is at most lambda over 1 minus lambda. So this is like a one-sided. For the two-sided, you can get the same thing. The lower bound on the spectral expansion actually improves as you go down. The upper bound deteriorates. Specifically, if you showed like that lambda was 0, which like is very tight, then you will still get a 0 here. If lambda is even slightly positive, this like gets worse and worse. But like the point is still that if you know that links here expand, then and the underlying graph here is connected, then links here will also expand, and you can sort of trickle down the expansion.
This is tight.
Yes, this is tight. I mean, there are simplicial complexes where this is tight. There are simplicial complexes where, I mean, when you say tight, it depends on what you mean, but there are simplicial complexes where analyzing the spectrum directly will give you something better than you get from this theorem. But like in general, you won't be able to improve that. So maybe I will just finish by saying, like we had here this like nice story where we talked about random walks. We saw what is like the maybe right definition or one right definition to maybe argue about them. And then we saw that this definition is like also a good idea because it's sort of amenable to this local to global analysis, like in at least in many interesting cases. There are like areas in high dimensional expansion that I actually haven't touched upon that are like equally interesting. One area is like construction. Now maybe I want, I don't care where my high dimensional expander came from, but I want certain properties. For example, like sparsity, like that every vertex will be connected only to a bounded number of edges, which is what we call bounded degree. And like here there are constructions. I mean, Alex here in the audience constructed high dimensional expanders before like the definition was actually given. All the constructions use like very highly non-trivial group theory, and I think it's like a very interesting open question or challenge to actually construct a bounded degree high dimensional expanders without using any sort of like group theory, only by like combinatorial means, or maybe like doing a random model where you sample pieces or something like that. Another area that I haven't touched upon is like how to use high dimensional expanders maybe as gadgets for other things, or maybe how to sort of use them to prove less naive properties on the Johnson graph and so on, which I think is equally interesting. I think I'll finish here.
Questions?
You said that a random hypergraph is not an expander? Or-
Okay, so like, what do you mean by random, right? Like if you look at the Erdős Renyi like equivalent of this random model, there are actually a few ways to sort of generalize the Erdős Renyi, but like in the way that you want, like you need to have like a very dense graph model. You need to take P, like the number of neighbors every vertex will have to have is like square root n. If you go anywhere below that, like you won't be a good expander. So this is not going to even give you what Erdős Renyi gave you. If you try to define like a random regular hypergraph that's bounded degree, you won't get this type of a definition. I mean, think about it. You're looking at links, but you're bounded degree. What's like the probability that you will even get a vertex in the links that has like degree 2? It's like a very fortunate event that you can get even something like that. But I mean, I don't know, maybe there is a random model and we just haven't like thought about it yet.
Sparse random graphs or hypergraphs have empty.
There's no way to glue, you start from your favorite expander graph, which will be the hopeful link, the higher dimensional link, and you try to glue them somehow.
Yeah, that's a good question. I mean,
But this is what people do in buildings.
right,
Because
like Bas and Sarah have this like way that you can take any graph and make an infinite simplicial complex where that graph looks like the link.
Exactly.
But I mean, but what next? I mean, I want a finite simplicial complex. So like, how are you going to quotient it for me? I mean, it's a good question in general, right? I mean, I have my links. Now I want a finite simplicial complex that like every link looks like one of these graphs in my family. Right? Even if you don't care about high dimensional expanders, I have neighborhoods of vertices and I want a graph where every neighborhood looks like one of these. And like for very certain types of graphs, we know how to do this for infinite graphs, but like it's a very challenging question, right?
The question.
So in all of these constructions, usually you fix the dimension and then you take the degree to be large enough for everything to work. Is there a situation where you want to take high dimension and fixed degree?
I guess it depends on your application. Like the problem with the theory at its current state is that because people have been like so used to like saying I can always take the degree to be a constant but large enough so it will like beat the dimension, and like really all the bounds that you know how to prove, they deteriorate the dimension. Like even the equivalence theorem that I wrote here that's not here anymore, it depends on dimension. When the dimension gets large, this is the question, like both you know how to prove less, and it also somehow becomes harder because you can't use this induction anymore because you're gaining error in one way or another. That being said, I mean it could be. I mean sometimes you have other reasons to like increase the dimension, but maybe you only care about like the low levels in terms of expansion, and then you don't care about like the fact that your degree is independent of dimension.
You want to say something about the relation of this definition, the random walk definition, to other definitions of high-dimensional expanders, even without defining them? Is it stronger than other definitions?
It's
other definitions. Or what?
Yeah, so it depends on what you mean by other definitions.
Comparative expansion.
Yeah, so like these topological definitions, they're non-equivalent. You can both define you can sort of like define what's called coboundary expanders, which are like something that has to do like with property testing of like the discrete cohomology of the simplicial complexes, and you can create coboundary expanders that are not expanders in this definition. You can create expanders in this definition that are not coboundary, or even like the weaker definition of like cosystole expanders.
But Kaufman and Evra shows that the spectral
Yes. So
local is a cycle expander, no?
what Kaufman and Evra show that if locally you are a co-boundary expander and you are a spectral expander, then globally you are also a co-boundary expander. But you have to start from like some co-boundary expansion that you know how to prove with other means. This is also maybe like a trickle-down theorem where you use like spectral expansion, but it's only like an auxiliary. You really need like the local things to be good co-boundary expanders, like inherently, at least in their proof. Like you can very easily show that you can have something that's not a co-cycle expander, but it still is like a random walk expander. Sort of you just sort of remove all triangles to like enforce a co-cycle, and then you just put one back or something.
Maybe one more thing you can say in general. I mean, what are your favorite applications so far? So people know what it's used.
Yeah, so those of you, that's a good comment. Those of you who like know, those of you who saw like my talk at the beginning, like I'm very interested in this like agreement proper testing problems where you sort of define local functions that are defined only on the faces. And it turned out that in some cases, using like high dimensional expansion and other properties, you can sort of glue them together to like one global function. This is sometimes called like the direct product testing or direct product encoding or decoding for those of you who've heard of it. I don't have a favorite actually. I mean, I also think that like applications of these like high dimensional notions of expansion to like error correcting codes are interesting. And like you can think about maybe a lot of problems, like maybe the most aspiring thing that I like am thinking about nowadays is to actually sort of replace places where like people use this like complete complex with high dimensional expanders to actually create PCPs that like don't need anything else but like some notion of high dimensional expansion. But this is still like, it's not that I have like an idea in my head of how to do it. You sort of still, I think, need to build some theory behind it before you can like do something like that. But like,
So well, I guess one should mention the local testing that big application as well. Even though it's not, well, I guess inspired by high dimension.
Yeah. I mean,
at the end of the day, it doesn't really need high dimension.
Right. In the end of the day, it's like the local, like these, I'll say relatively new, what they're like 2021, I think. The people constructed like locally testable codes that had like very good rate and like constant rate and constant distance, which was like a major breakthrough, I think, in coding theory. Like people conjectured that these things didn't even exist. And like, it's not that these constructions use high dimensional expanders per se, but they still use like this interesting idea both of like this poset structure of like having several layers and sort of defining a Tanner graph using both layers. And they also use like this notion of like analyzing things by viewing the links. So the links are not exactly expanders there. There's also like a very intricate definition, but like at least in spirit, ideas that maybe we saw here are maybe are like connected to this. Like Alex, do you have any comments about this?
No, that's what we did, but certainly it started with a great belief that high-dimensional expansion is a form of properties testing that are intimately connected. Nowadays, we know say it in several different ways.
Yeah.
I think maybe you addressed this, but I got confused about something. So you said you proved that expansion implies local expansion?
Yeah, that is like random walk definition implies the local expansion in all links and vice versa.
And then I guess for graphs, this isn't true, right? For graphs?
Well, like in a very silly way, right? Because like for graphs, the only link that has like a graph structure in it is like the link of the empty set, which is the whole graph. So like in a graph, both of these definitions are just equivalent to like the two-sided expansion. Like because the random walk definition said that the adjacency operator is similar to the independent operator. And like in the links, you say that in the links you're an expander, but your only link is like the whole graph. So like in graphs, this is not very interesting.
Right, good, thanks.